And hopefully you can tell that the chemical formula of silver carbonate is not AgCO3, because +1 is not going to be balanced with a -2 charge for the carbonate ion, but instead, to balance that chemical formula for silver carbonate, I need 2 silvers, and each silver has a charge of +1 for every 1 carbonate ion. So the correct chemical formula for silver carbonate is actually Ag2CO3. Now let's take a look at choice A in question 3. Welcome to AP Chemistry Review and Practice. My name is Michael Farabaugh, and I'll be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Each episode will include answers and explanations to practice problems, along with advice to help you avoid common mistakes. So, are you ready to review and practice for the AP Chemistry exam? I hope so, because this lesson starts right now. Welcome back to AP Chemistry Review and Practice. In this lesson, I'll give you the chance to review and practice topics 4.1 to 4.4. As you can see on this slide, these topics fall under Unit 4 in the AP Chemistry curriculum, Chemical Reactions. You can add your comments and questions below this video, and you can also email me with your comments and questions at apchemistryreviewandpractice@gmail.com. Check out the links in the video description area, which include the link to the packet that accompanies this video. Now let's move on to the review for Topic 4.1, Introduction for Reactions, and Topic 4.4, Physical and Chemical Changes. I have decided to combine these two topics together because their essential knowledge statements are very similar to each other. So here are the essential knowledge statements from the AP Chemistry course and exam description. A physical change occurs when a substance undergoes a change in properties, but not a change in composition. Changes in the phase of a substance, solid, liquid, or gas, or formation or separation of mixtures of substances are common physical changes. A chemical change occurs when substances are transformed into new substances, typically with different compositions. Production of heat or light, formation of a gas, formation of a precipitate, and/or color change provide possible evidence that a chemical change has occurred. Processes that involve the breaking and/or formation of chemical bonds are typically classified as chemical processes. Processes that involve only changes in intermolecular interactions, such as phase changes, are typically classified as physical processes. Sometimes, physical processes involve the breaking of chemical bonds. For example, plausible arguments could be made for the dissolution of a salt in water as either a physical or a chemical process, involves the breaking of ionic bonds and the formation of ion-dipole interactions between ions and solvent. Now let's move on to the practice for topics 4.1 and 4.4. This is question 1. In question 1, we are presented with 4 different sets of particle diagrams, and the question asks which of the following particle diagrams is the best representation of a process that is classified as a physical change. So, since only one of these 4 choices would be correctly classified as a physical change, that means that the other 3 processes would be classified as a chemical change. And remember that a physical change occurs when a substance undergoes a change in properties, but not a change in composition. Let's look more closely at the particle diagram. So in the particles in the diagram on the left, I see molecules in which one black circle is bonded to 2 gray circles. But in the particle diagram on the right, I see individual atoms of either black or gray circles. So we can say with confidence that this is likely to be a chemical change in choice A because we can see a different chemical composition of the particles at the start and the end of the process. Now let's move on to choice C. Again, similarly, I can see a molecule on the left in which there's a black circle bonded to two gray circles, but in the particle diagram on the right, I see some elements in which two gray circles are bonded together. I can also see some compounds in which I have a black circle bonded to a gray circle. So again, just like in choice A, we can see a different chemical composition of the particles at the start and the end of the process. So choice C also looks like it should be classified as a chemical change. Now, moving on to choice D. So again, in choice D, I can compare the particles in the diagram on the left and the right. And in the left, I can see molecules in which one black circle is bonded to two gray circles. But in the particle diagram on the right, I can see individual diatomic molecules in which either two gray circles are touching or bonded together, two black circles are touching and bonded together. So again, in choice D, we can see a different chemical composition of the particles at the start and the end of the process. So now that I've eliminated choices A, C, and D, let's go back and take a closer look at choice B. So these 8 molecules in which one black circle is bonded to two gray circles appears in the diagram on the left, and those same 8 molecules with the same chemical composition are simply spread out. So it's likely that this would represent a phase change from perhaps a solid to a gas, but we do not see a different chemical composition in these two diagrams. So in choice B, we can see the same chemical composition of the particles at the start and the end of the process. So that makes choice B the most likely to represent a physical change. Now let's take a look at question 2. In question 2, we can see that we are given a balanced chemical equation, and then we also have a description of a laboratory experiment. It says, a student added a 5.0 gram sample of solid NaHCO3 to a steel crucible and then heated the crucible on a hot plate at 250 degrees Celsius for 15 minutes. The student made the claim that during the process of heating the sample of solid NaHCO3, a chemical reaction occurred according to the equation shown above. So we can see that on the right side of the equation, we have another solid with a different chemical composition. It's Na2CO3. And then we can also see H2O, gas, so water vapor. And then we can see CO2, also a gas, that's carbon dioxide gas. Now, which of the following observations about the solid present in the crucible at the end of the experiment provides the best evidence to support the claim that this particular chemical reaction has taken place? So in this question, we are focusing our attention on the properties of the solid that is present in the crucible at the end of the experiment. I will begin with choice A. So choice A says that the solid is soluble in water. Well, the problem with choice A is that we really should be comparing what we started with what we ended with. So in this chemical equation, it does begin with a solid and then ends with one solid and two gases. But specifically, the properties of the solid product, Na2CO3, such as its solubility in water, is not specific evidence to prove that a chemical reaction has occurred. So, for example, if the chemical that we started with, NaHCO3, was soluble in water, then how do we know that after heating this sample at 250 degrees Celsius for 15 minutes, it's possible that we still have the same solid that we started with? So what we really need to do is make more of a comparison, not just look at one property of one substance at the end of this experiment. So I'm going to eliminate choice A, and then I'll remind you that a chemical change occurs when substances are transformed into new substances. So we need some evidence that something has occurred causing a change from one substance to another. So typically, these new substances are going to have different compositions and different properties. Another clue that can provide possible evidence that a chemical change has occurred would be production of heat or light, formation of a gas, formation of a precipitate, and or a color change. Now on this slide, you can see a hot plate, and then you can see a picture of a crucible with some solid in it. So that would be the chemical that we started with, the solid NaHCO3. Now then, there was a period of time in which this was heated at 250 degrees Celsius for 15 minutes, and if in fact this chemical reaction did occur according to this balanced chemical equation, then the solid that's present in the crucible at the end of the experiment would not be NaHCO3 solid, but rather a solid with a different chemical composition, Na2CO3 solid. So one way to provide support for the claim that this particular chemical reaction has taken place is to compare the properties of NaHCO3 solid, which is the chemical that we started with the properties of Na2CO3, which is the solid that should be present in the crucible at the end of the experiment. So if you consider that choice A just talked about the solubility of the solid in water at the end of the experiment, that's not really a comparison between what we started with and what we ended with. In choice C, it says the solid does not conduct electricity. In choice D, it says the solid starts to melt when it is heated to a temperature of 850 degrees Celsius, but they're just talking about the solid present at the end of the experiment. There is no comparison. So in choices C and D, there is no comparison between the properties of the solid reactant, NaHCO3, and the properties of the solid product, Na2CO3. So I'm going to eliminate choices C and D because there is no comparison of properties. Now I have to give you a good reason why choice B is the best and correct answer to question 2. And so what I'm going to do is focus on the gases that were produced in this chemical reaction. So we started with a solid, and then we end with a different solid with a different chemical composition, but there's also water vapor, so H2O gas, and CO2 gas, or carbon dioxide gas, that would be given off during the heating process. Notice that the crucible is open to the air, and if gases are produced during this experiment, then they would simply leave the open crucible. So another way to provide support for the claim that this particular chemical reaction has taken place is to compare the mass of the container and its contents before the reaction and after the reaction. So it said that we began with 5.0 grams of solid NaHCO3, and if we ended with exactly 5.0 grams of solid, then that would not provide very much evidence to support that a chemical reaction has taken place. But if the gases are released during this particular chemical reaction, then those gases would be lost to the air, and the final mass of the solid should be less than 5.0 grams. And so that's why choice B is the correct answer. So if the solid that is present in the crucible at the end of this experiment is 3.2 grams, in other words, if it weighs less than 5.0 grams, that would provide evidence that perhaps during this chemical reaction, gases were released, and that would explain the loss of mass. Well, hopefully that makes sense. Now it is time to move on to the review for topic 4.2, net ionic equations. Here are some essential knowledge statements from the AP Chemistry course and exam description. All physical and chemical processes can be represented symbolically by balanced equations. Chemical equations represent chemical changes. These changes are the result of a rearrangement of atoms into new combinations. Thus, any representation of a chemical change must contain equal numbers of atoms of every element before and after the change occurred. Equations thus demonstrate that mass is conserved in chemical reactions. balanced molecular, complete ionic, and net ionic equations are differing symbolic forms used to represent a chemical reaction. The form used to represent the reaction depends on the context in which it is to be used. Now let's move on to the practice for topic 4.2. This is question 3. In question 3, it says, a student combines a solution of silver nitrate, which has the chemical formula AgNO3, with a solution of sodium carbonate, which has the chemical formula Na2CO3, and a solid precipitate is formed. Which of the following is the balanced net ionic equation for the reaction that occurs when these two solutions are combined? Now, before I consider the 4 choices in question 3, I just want to remind you of what are called monoatomic ions as well as polyatomic ions. Now, this is information that I had shared in my YouTube video that includes topic 4.2, net ionic equations. So here on this slide, you can see some examples of monoatomic ions, and you can see I've got charges listed for 1+, 2+, 3+, 3-, 2-, 1-. If you look on the periodic table, there are some general patterns about the charges of monoatomic ions. For example, the elements in group 1 normally form ions, monoatomic ions, with a charge of 1+, and then group 2, 2+ monoatomic ions. And then the boron family in group 13, boron aluminum, 3+. Then you can see the nitrogen family, the oxygen family, the halogens, 3-, 2-, 1-. So again, these are general patterns of monoatomic ions. Now, with respect to polyatomic ions, there are many polyatomic ions, but I'm going to give you some common polyatomic ions that I think would be good for AP chemistry students to be familiar with. So I'll start with +1 or 1+. So the ammonium ion has the chemical formula NH4, and it has a charge of 1+. And then here are 2 examples of polyatomic ions that have a charge of -1 or 1-, and that would be the hydroxide ion, so OH -1, and the nitrate ion, NO3 -1. Here's a couple of examples of polyatomic ions that have a charge of 2- or -2. Carbonate, CO3 2-, sulfate, SO4 2-, and then phosphate, PO4, has a charge of 3- or -3. Also in my video for topic 4.2, net ionic equations, I had mentioned what are called sodium, potassium, ammonium, and nitrate salts that are soluble in water, and I refer to them as the, quote, SNAP ions, where SNAP is an acronym, and the letters SNAP refer to these ions. S for sodium, N for nitrate, A for ammonium, and P for potassium. So all ionic compounds, or salts, that contain one of these ions are considered to be soluble. Now, back to question 3. A student combines a solution of silver nitrate, which has the chemical formula AgNO3. Now, you should know from experience that the nitrate ion is NO3 -1. So what's the charge on the silver ion if I have a 1-to-1 ratio between silver and nitrate in the compound silver nitrate? Silver would have to be +1 since it's got a 1-to-1 ratio with the nitrate ion. So +1 for silver, -1 for nitrate. Now with sodium carbonate, there are 2 sodiums, and based on where you can find sodium in group 1 on the periodic table, if I have 2 sodiums and each sodium is worth +1, that means that the charge on the carbonate ion has to balance the charge on 2 sodium ions. So if you don't remember that the carbonate ion is CO3 2-, you can tell in that chemical formula for sodium carbonate that the CO3 has to have a charge that balances the charge on the 2 sodiums. Now let's go ahead and take a look at the chemical formulas of the products of this particular precipitation reaction. So I'll start with silver. Silver is now combined with carbonate to produce the product silver carbonate. And hopefully you can tell that the chemical formula of silver carbonate is not AgCO3, because +1 is not going to be balanced with a -2 charge for the carbonate ion, but instead, to balance that chemical formula for silver carbonate, I need 2 silvers, and each silver has a charge of +1 for every 1 carbonate ion. So the correct chemical formula for silver carbonate is actually Ag2CO3. Now let's take a look at choice A in question 3. Notice that they have the wrong charge on carbonate. It's -1 instead of 2-. And the chemical formula of silver carbonate should be Ag2CO3, not AgCO3, which means we can eliminate choice A. And then similarly, if you take a look at choice C, on the right side of that chemical equation, they've written AgCO3, which is incorrect, and also Na2NO3 is another example of an incorrect chemical formula, so we can eliminate choice C. So NaNO3, or sodium nitrate, because sodium is +1 and nitrate is -1, that chemical formula should be NaNO3. Now I'm going to balance this chemical equation. So I need 2 silver ions on the left side of this equation. So I'm going to add another copy of the silver nitrate formula. And then I need 2 sodium ions on the right side of the equation. So I'm going to add another copy of the sodium nitrate formula on the right. Now what you're looking at in choice D is not the correct answer to question 3. But what you are looking at is a correctly balanced equation for the precipitation reaction that occurred in this experiment. But this is the molecular equation. And so if you read the question carefully, it says, which of the following is the balanced net ionic equation? So if you're watching this video and you're not sure what's the difference between the molecular equation and the net ionic equation, this is something that I had mentioned in my YouTube video that includes Topic 4.2, Net Ionic Equations. So on this slide, you can see an example of a precipitation reaction. A precipitation reaction occurs when 2 different aqueous solutions containing ions are combined, resulting in the formation of an insoluble or slightly soluble solid ionic compound. The solid product is called the precipitate. So you're seeing a picture on this slide of the formation of a bright yellow precipitate that happens to be lead iodide. Now, there are 3 different ways to write a balanced equation for a precipitation reaction. The first is what I had shown you in choice D, which is called the molecular equation. So in the molecular equation, each reactant and product is written as a neutral compound, but the formulas are not split up into separate ions. In the complete ionic equation, any substance that ionizes completely is broken up into separate ions. Any substance that does not ionize or is only partially ionized is written as a neutral compound, and then you get what are called spectator ions, ions that appear in identical forms on both sides of a complete ionic equation. And now we come to what we're looking for in question 3. The net ionic equation, that is the balanced equation that describes the actual reaction that occurs in aqueous solution, and it is obtained after the spectator ions are eliminated from the complete ionic equation. So for this reaction that you're looking at, the picture of the formation of the bright yellow precipitate of lead iodide, that was featured in my video for topic 4.2, net ionic equations. So there's the molecular equation for the formation of the lead iodide, the solid bright yellow precipitate. So you can see that I haven't broken up anything into ions. This is the complete ionic equation where I split up the potassium iodide into potassium ions with the charge on potassium, iodide ions with the charge on iodide, and I also split up the lead nitrate. So I have lead ions with its charge, I have nitrate ions with its charge, and on the other side of the equation, I split up the potassium nitrate, so I have potassium ions and nitrate ions on the right side of the equation. But you'll notice I did not split up the solid lead iodide on the right side of the equation. Because it's a solid, it won't be broken up into separate ions because it's not dissolved in the solution. And now hopefully you can see that on the left side and the right side of this complete ionic equation are potassium ions, which I'm crossing off on both sides, and nitrate ions, which I'm crossing off on both sides. Those are the spectator ions. And now that I've eliminated the spectator ions from the complete ionic equation, this is the net ionic equation to show that the iodide ions combined with the lead ions to produce that bright yellow precipitate, solid lead iodide. Now, back to question 3. We know that choice D is the molecular equation. I'll go ahead and eliminate choice D. And now I'll show you why choice B is the correct answer to question 3. So I'm going to split up the silver nitrate into silver ions and nitrate ions. I'm going to split up the sodium carbonate into sodium ions and carbonate ions. I'm not going to split up the silver carbonate precipitate. But since the compound sodium nitrate contains at least one of those soluble snap ions, that means that sodium nitrate is a soluble ionic compound, and I'm going to split it up into sodium ions and nitrate ions. I will cross off my spectator ions, which are the sodium ions and the nitrate ions on the left side and the right side of my complete ionic equation. And then what I have left behind is in fact the correct answer to question 3, the net ionic equation for the formation of solid silver carbonate in this experiment. Well, hopefully that makes sense, and we're going to see another example of a precipitation reaction in question 4. So now it is time to take a look at question 4. Now, what makes question 3 and question 4 in this packet very similar is that they both involve a precipitation reaction. But what makes question 4 different than question 3 is that question 3 was a multiple choice question. All we had to do in question 3 is pick the correct answer. In question 4, we will need to write the correct balanced molecular equation for this precipitation reaction, and we will also need to write the correct balanced net ionic equation. So I will guide you through each step of the process. Now, it begins by giving us a description of what happened in this experiment. It says, a student combined a solution of magnesium nitrate, which has the chemical formula Mg and then NO3 in parentheses times 2, with an excess amount of aqueous potassium phosphate, which has the chemical formula K3PO4, as represented above, and observed the formation of a precipitate. So in part A of this question, to get us started, it says in the table below, circle the correct charge for each ion that is present in the solutions that were combined in this experiment. And I can see in the table that we have the magnesium ion, the nitrate ion, the potassium ion, and the phosphate ion. Now, 2 of these ions are monoatomic, so I'm going to start with the monoatomic ions. If I look on the periodic table and I know that magnesium is located in group 2, I expect the charge on the magnesium ion to be +2 or 2+. I can see that potassium is located in group 1, so I would expect the charge on the potassium ion to be +1 or 1+. So magnesium is a 2+ monoatomic ion, and potassium is a 1+ monoatomic ion. Now, do we need to memorize the charge on nitrate, or can we figure it out just by the given information in question 4? So here is the chemical formula of magnesium nitrate. We can see that for every 1 magnesium ion, there are 2 nitrate ions. And if we know that the charge on the magnesium ion is 2+, and we have 2 nitrate ions in that chemical formula, then each nitrate ion should have a charge of -1. Therefore, my correct ionic formula has magnesium with a charge of 2+, and 2 nitrate ions, and each of the nitrate ions has a charge of -1 or 1-. Now we'll do a similar strategy for potassium phosphate. So we are given a chemical formula that is written as K3PO4. So I have 1, 2, 3 potassium ions, and each charge is +1. So that means I need the charge on the phosphate ion to be -3 or 3-. So 3 potassiums, and each potassium ion is +1, 1 phosphate ion, and the charge on the phosphate ion is -3 or 3-. Now that we have answered part A, we're going to take a look at what the student wrote for the chemical formulas of the products of this precipitation reaction in part B. Let's take a look at part B. It says the student is preparing to write the molecular equation for the reaction that occurred in this experiment. So the student wrote a chemical formula of MgPO4 for magnesium phosphate, and the student wrote a chemical formula of KNO3 for potassium nitrate. Now in part B, it says only one of the student's chemical formulas is correct. So based on your answers to part A, in which we have determined already the charges on all of the ions, it says circle the one correct chemical formula that was written by the student. So magnesium nitrate was already given to us as Mg and then NO3 in parentheses times 2. Potassium phosphate was already given to us as K3PO4. And so now let's go ahead and combine the magnesium ion, which is 2+, with the phosphate ion, which is 3-. And just like we saw in question 3 of this packet, where silver carbonate was written incorrectly in one of the choices, and we could eliminate AgCO3 as an incorrect chemical formula, we can tell that the student's MgPO4 is incorrect because the charges do not balance each other out. Now, if I have 2 magnesiums and 1 phosphate, the charges still do not balance out. If I have 2 magnesiums and 2 phosphates, nope. But finally, if I have 3 magnesium ions, that would be a total charge of +6. And if I have 2 phosphate ions, that would give me a total charge of -6. So what is the correct chemical formula of magnesium phosphate? It is Mg3 and then PO4 in parentheses times 2. I'm going to eliminate that as a possible answer to part B. It says only one of the student's chemical formulas is correct, and so that means that potassium, which is +1, and nitrate, which is -1, would be written as KNO3. So the student wrote potassium nitrate correctly, but they wrote magnesium phosphate incorrectly. Now, before we take a look at part C of this question, in which we have to write the correct balanced molecular equation, let's go ahead and finish off this particle representation with the little rectangles for this balanced equation. I need 1, 2, 3 magnesium ions on the left side of the equation to balance the 3 magnesium ions on the right side of the equation. And then I need not just 1, but 2 phosphate ions on the left side of the equation to balance the 2 phosphate ions on the right side of the equation. Now, how many potassium ions do I see on the left side? I see 6. How many nitrate ions do I see on the left side? Also 6. So I need a total of 6 potassium nitrates on the right side of the equation. I'm going to convert all of these rectangles into a balanced chemical equation. So it's going to be 3 in front of the correct chemical formula for magnesium nitrate. It's going to be 2 in front of the correct chemical formula for potassium phosphate. And then we don't have a coefficient for magnesium phosphate, so it's understood to be a 1. But there's the chemical formula for magnesium phosphate, Mg3, and then PO4 in parentheses times 2. And then I have a 6 in front of the correct chemical formula for potassium nitrate. Now, if you're wondering, what are those question marks? Well, we haven't determined the identity of the precipitate, and I'm going to go ahead and add an AQ for the aqueous or the soluble ionic compound, and I'm going to add an S to indicate the solid precipitate. So if you remember your soluble snap ions, they are S for sodium, N for nitrate, A for ammonium, and P for potassium. Since potassium nitrate contains at least one of those soluble snap ions, that means that potassium nitrate will be soluble. So this is not the precipitate, and therefore by default, the precipitate is the magnesium phosphate. So what you're looking at the top of this slide is the correct answer to part C of this question. This is the molecular equation. So in part C, write the correct balanced molecular equation for the precipitation reaction that occurred in this experiment, and there it is. Now there's only one more part of this question, so what we have to do is convert the molecular equation into the balanced net ionic equation. I'm going to split up the magnesium nitrate into 3 magnesium ions and 6 nitrate ions. And that's because the coefficient of 3 is in front of the magnesium nitrate, so that serves as a multiplier. I'm going to split up the potassium phosphate, based on that coefficient of 2, into 6 potassium ions and 2 phosphate ions. Now I'm done with the left side of the equation. On the right side of the equation, because the magnesium phosphate is a solid, so I will just write that chemical formula as one chemical formula, not split up into separate ions. But then with the 6 in front of the potassium nitrate, I'm going to split that up, the aqueous potassium nitrate, into 6 potassium ions and 6 nitrate ions. What I have just written is not my final answer for part D. This is the complete ionic equation. Now it's time to cross off the spectator ions. So I see 6 nitrate ions on the left and on the right, and I see 6 potassium ions on the left and on the right. So after I cross off my spectator ions from both sides of the equation, my final answer to part D is the following. This is the correct balanced net ionic equation for the precipitation reaction that occurred in this experiment. Notice that I have it balanced, so 3 magnesiums and 2 phosphates on the left, 3 magnesiums and 2 phosphates on the right, and I'm showing the correct charges on my aqueous ions on the left side of the equation. So now that we are done with question 4, I hope that the answers to question 4 make sense to you. It is time to move on to question 5 in the packet. In question 5, we can see a diagram with some beakers, and we can see a description of a laboratory experiment. In question 5, it says, hydrochloric acid, which has the chemical formula HCl, is an example of a strong acid that completely ionizes in aqueous solution according to the equation shown below. And we can see the chemical formula HCl, which splits up into H+ ions and Cl- ions. And the hydrochloric acid is in the beaker that is shown on the left side of this diagram. The description of the laboratory experiment goes on to say that a sample of solid aluminum, which we can see present above the beaker, it's about to be added to the beaker of hydrochloric acid, a sample of solid aluminum is added to a beaker containing an excess amount of aqueous hydrochloric acid, as shown in the diagram above. A chemical reaction occurs, resulting in the formation of hydrogen gas, and we can see that after the aluminum is added to the beaker, there are bubbles of gas forming on the surface of the aluminum. So that's hydrogen gas being produced. And at the end of the experiment, the beaker contains a mixture of aqueous AlCl3, that's aluminum chloride, and then HCl, hydrochloric acid. So because there was an excess amount of hydrochloric acid, there is still some leftover unreacted hydrochloric acid in the beaker, along with aluminum chloride, that's AlCl3. Now, we have a multiple choice question, and it says, which of the following is a balanced net ionic equation that represents only the species that react and the species that are produced in this experiment? I will start with choice A. So we have a sample of solid aluminum is added to a beaker, and I can definitely see solid aluminum as a reactant in choice A. And then that beaker contains an excess amount of aqueous hydrochloric acid, and I can see HCl aqueous on the left side of the equation as a reactant in choice A. Now, what about the products? Well, a chemical reaction occurs resulting in the formation of hydrogen gas, and I can see the chemical formula of hydrogen gas on the product side of the equation in choice A. It also says at the end of the experiment, the beaker contains a mixture of HCl and AlCl3, which I can see on the product side or the right side of the equation. So looks like choice A does have a balanced equation, 2Al plus 6HCl, and it produces 2AlCl3 plus 3H2. So choice A is a correctly balanced equation. However, choice A is not the correct answer to question 5. So what's wrong with choice A? It's correctly balanced, but it represents the molecular equation. And this question said, which of the following is the balanced net ionic equation? So choice A is the molecular equation. We still haven't found the balanced net ionic equation. Now, one question we have to ask ourselves is, do I split up a chemical formula into separate ions, or do I leave it unchanged? Take a look at aluminum in this equation. Aluminum is a solid. Take a look at hydrogen. Hydrogen is a gas. If you have a gas, such as hydrogen, if you have a liquid, such as H2O, or a solid, such as solid aluminum, then we leave that chemical formula unchanged. What about the AlCl3? That contains a metal and a nonmetal, and so therefore that is an aqueous ionic compound. We will split up aluminum chloride into separate ions, aluminum ions and chloride ions. And what about the chemical formula HCl? We were already given information that hydrochloric acid is an example of a strong acid that completely ionizes in aqueous solution, so that will be split up into separate ions. So aluminum is a solid, don't split it up. HCl is a strong acid that completely ionizes in aqueous solution, so we will split it up. Aluminum chloride contains a metal, aluminum, and a nonmetal, chlorine. That's an aqueous ionic compound, so we'll split that up into separate ions. And then hydrogen is a gas, so we'll leave that unchanged and not split it up. So 2Al solid, but now I'm going to split up the HCl, and there's a 6 as the coefficient. So it's going to be 6 H plus ions and 6 Cl minus ions. And on the other side of the equation, that would be 2 aluminum ions, which have a charge of +3, and 6 chloride ions, so 6 Cl minus. Hydrogen is a gas. I'm not going to split it up, so +3H2. Now, do we see any spectator ions that appear in identical forms on the left and the right? I see 6 chloride ions on the left, and I see 6 chloride ions on the right. I'm going to cross off my spectator ions, and now I have the correct answer. I have the correct net ionic equation. Let's go look for the correct net ionic equation among the choices B, C, and D. Well, choice B is close, but I can see 6 chloride ions on the left, and I also see 6 chloride ions on the right. So in choice B, that is the complete ionic equation, but they forgot to cross off the spectator ions on opposite sides. Choice C looks pretty good. This is the correct net ionic equation. And then choice D, it shows AlCl3 written as one formula. That's an aqueous ionic compound, which should be split up into separate aqueous ions. That makes choice D incorrect. Correct answer to question 5, the correct net ionic equation, is choice C. All right, well, hopefully that makes sense. Now let's take a look at question 6. In question 6, we are given a correctly balanced chemical equation, but the question asks, which of the following is the correct net ionic equation for the equation shown above? So I'm going to ask that same question I asked in question 5. Do I split up the formula into separate ions or leave it unchanged? If I see a solid or a liquid or a gas, I will leave it unchanged. If I see an aqueous ionic compound, I will split it up into separate ions. So iron, Fe, is a solid, so don't split it up. The copper chloride contains a metal, copper, and a nonmetal, chloride. That's an aqueous ionic compound, so we will split it up. Copper on the other side of the equation is written as a solid, so don't split it up. And then iron and chlorine. That's a metal and a nonmetal. FeCl2 is an aqueous ionic compound, so we will split it up. Now the charge on the chloride ion is -1. So I'll start with iron. As a solid, I don't split it up. If the chloride ion is -1 and we have two of them in that formula, that means that the charge on the copper ion is +2. So two chloride ions, -1 each, one copper ion with a 2+ charge. On the other side of the equation, I'm not going to split up the solid, but then I have, again, two chloride ions, so the iron on that right side of the equation is also a +2 ion. So iron with a 2+ charge and two chloride ions that each have a -1 charge. Let's cross off the spectator ions on the left and the right. I see two chloride ions on the left. I see two chloride ions on the right. And so there is my correctly balanced net ionic equation. So now that we know the correct net ionic equation, let's choose the correct answer. Now choice A is very close, but incorrect. The correct charge on the copper ion on the left and the charge on the iron ion on the right is not +1, but +2. So what makes choice A incorrect is that it has the wrong charges on the ions. Choice B is the correct answer. And the reason why choices C and D are incorrect is because FeCl2 is an aqueous ionic compound, and that formula should be split up into separate ions. Also, solid copper is a product, and that should be shown on the right side of the equation, but it's not listed in choices C and D. So correct answer to question 6, the correct net ionic equation, is choice B. All right, well, hopefully that made sense. And now it is time to move on to the review for topic 4.3, representations of reactions. Here is a very brief, essential knowledge statement from the AP Chemistry course and exam description. And that is, balanced chemical equations in their various forms can be translated into symbolic particulate representations. All right, well, now it's time to move on to the practice for topic 4.3. This is question 7. In question 7, we can see a particle diagram above the question, and the question says, a mixture of CO, which is carbon monoxide gas, and O2, which is diatomic oxygen gas. That mixture is placed in a reaction vessel as shown above. So we can see that the black circles represent atoms of carbon, and the white circles represent atoms of oxygen. Now, a reaction between carbon monoxide and O2, or oxygen gas, occurs, forming CO2, or carbon dioxide gas. Now, the question asks, which of the following best represents the contents of the reaction vessel after the reaction has proceeded as completely as possible? Now, before I analyze the 4 particle diagrams that are listed in question 7, the first thing I'm going to do is write a balanced chemical equation for the reaction described in question 7. So we have CO reacting with O2 to produce CO2. Here is my unbalanced chemical equation. I see one atom of carbon on the left, one atom of carbon on the right. I see 3 atoms of oxygen on the left and only 2 atoms of oxygen on the right. So I'm going to put a coefficient of 2 in front of the carbon dioxide on the right side of the equation. Now on that right side of the equation, I have 2 atoms of carbon and 4 atoms of oxygen. So I'm going to balance the carbon atoms by putting a 2 in front of the carbon monoxide on the left side of the equation. And now this equation is balanced. I have 2 atoms of carbon on each side of the equation, and I have a total of 4 atoms of oxygen on each side of the equation. Now, before I look at the particle diagrams in question 7, I'm going to see if I can create this just based on the mixture that was placed in the reaction vessel. So, for every 2 molecules of CO that react with 1 molecule of O2, it's going to produce 2 molecules of CO2. So for every 2 molecules of CO that react with 1 molecule of O2, it's going to produce 2 molecules of CO2. And I'm showing a CO2 molecule as a black circle touching two white circles. I'm going to do that one more time. For every 2 molecules of CO that react with 1 molecule of O2, it will produce another 2 molecules of CO2. But at this point, I have run out of one of the reactants. So I don't have any more molecules of carbon monoxide or CO, but I still have 2 unreacted or leftover or excess molecules of O2. I can't throw them away. Because of the law of conservation of mass or the law of conservation of atoms, those 2 molecules of O2 would still appear in the reaction vessel after the reaction has proceeded as completely as possible. So I kept going until I used up all of the molecules of the reactant CO, and then I added those 2 excess or leftover molecules of O2 to obey the law of conservation of matter or the law of conservation of atoms. So what am I looking for as the correct answer to question 7? The correct answer is a particle diagram that contains 4 molecules of CO2 and 2 molecules of O2. So that makes the correct answer to question 7 choice C. So 4 molecules of CO2 are produced, and then 2 molecules of O2 are left over at the end after all of the carbon monoxide was consumed, as the reaction has proceeded as completely as possible. All right, well, hopefully that answer makes sense, and we have one more question in this packet. It's also a particle diagram question for topic 4.3. So this is question 8. Now, we don't have to choose the correct particle diagram. They're already given to us in this question. What we have to do is choose which of the following represents the correct balanced chemical equation for the reaction that occurred. So the white circles represent element X, the black circles represent element Y. So based on the information in the particle diagrams above, which of the following represents the correct balanced chemical equation for the reaction that occurred between X2 and Y2? Now, looking at the product mixture, there is 1 black circle, which is element Y, bonded to 2 white circles of element X. That means that the chemical formula of the product is actually written as X2Y, 2 white circles bonded to 1 black circle. So X2Y is not listed on the product side in choice A, and in choice B, it's listed incorrectly as XY2, which means we can eliminate choice A and choice B. Now, in choice C, it has X2Y as a product, but that equation is not balanced. There should be 4 atoms of X on the right, and they didn't put that coefficient in front of the X2Y. So we can eliminate choice C, and that makes choice D the correct answer. Now, if you counted the particles in the reactant mixture, I see 1, 2, 3, 4, 5, 6 molecules of X2, and I see 3 molecules of Y2. And when that reaction goes to completion, there are no excess or leftover reactants, as we saw in question 7, but it's going to produce 6 molecules of X2Y. Now, are the coefficients 6, 3, and 6? No, we can reduce that by dividing each of those numbers by 3, so the correct coefficients are not 6, 3, and 6, but rather 2, 1, and 2. And so that explains why, based on this particle diagram in question 8, the correct answer is choice D. All right, well, since this is the last question in the packet, now it is time to move on to that part of the lesson where I give you advice to help you avoid common mistakes. So the first thing I will mention is if you are looking for more practice problems on these topics, you can review the information in my video for topics 4.1 to 4.4, and that link is included in the video description area. My next piece of advice is what I normally say during this part of the lesson. Read the question carefully and make sure you are answering the question that is being asked. Be familiar with the difference between a physical change and a chemical change. It is important to use the data and observations from laboratory experiments as evidence to support the claim concerning a physical change or a chemical change. Be familiar with the charges on monoatomic ions, and you can review that in topic 1.8, which was from an earlier lesson for AP Chemistry Review and Practice. Be familiar with the formulas and charges of the following common polyatomic ions. And so I have ammonium, which is NH4 plus 1. I have hydroxide, which is OH minus 1. Nitrate, which is NO3 minus 1. Carbonate, which is CO3 minus 2. Sulfate, which is SO4 minus 2. And phosphate, which is PO4 minus 3. Now remember, if you are given the chemical formula for an ionic compound, and you know the charge on one of the ions, then you can use that information to determine the charge on the other ion. And I showed you examples of how to do that in this lesson. Now, with respect to writing net ionic equations, obviously it's good to practice writing net ionic equations and consider the following guidelines. Be familiar with the difference between a molecular equation and a net ionic equation. The formula of a gas, a liquid, or a solid should not be split up into separate ions. On the other hand, the formula of an aqueous ionic compound should be split up into separate ions. Make sure to include the correct charges on the ions. Cross off the spectator ions that appear on both sides of the equation. Make sure that the equation is balanced, not only in terms of the number of atoms of each element, but also in terms of the overall charge on each side of the equation. And if you need to write a balanced net ionic equation on the AP Chemistry exam, the symbols for the phases of matter, such as S for solid, L for liquid, G for gas, and AQ for aqueous, those symbols are not required in your response on the AP Chemistry exam. So they're a good idea, and I normally include those phases of matter, but on the AP Chemistry exam, you will not lose points for not including the symbols for phases of matter. Now, with respect to particle diagrams, obviously practice working with particle diagrams that represent chemical reactions, both writing them and interpreting them. Consider the following details. The stoichiometry of the reaction is connected to the coefficients in the balanced equation. These values determine the mole ratios between different substances and the process by which the reactants are converted into the products. Make sure that the particles in the diagram are the correct representations of the chemical formulas of the reactants and the products. And finally, make sure that the conservation of atoms is obeyed when comparing the particle diagram for the reactant mixture with the particle diagram for the product mixture. And make sure to identify the limiting reactant and the excess reactant. That's a very helpful tip. All right, well, now we have come to the end of this lesson. In my next lesson, I'll give you the chance to review and practice topics 4.5 to 4.6. If you enjoyed this lesson, I invite you to like this video and subscribe to my YouTube channel. Check out the links in the video description area, which include the link to my YouTube playlist organized by AP Chemistry CED units. You can add your comments and questions below this video, and you can also email me with your comments and questions at APChemistryReviewAndPractice@gmail.com. Thank you for letting me be your guide on the side as you strive toward that 5 on the AP Chemistry exam. Keep studying, and I'll see you next time on AP Chemistry Review and Practice.